Welcome back. Last time we talked about the MMMQ. Actually, before that, we also discussed two more systems like MM1 and MMMM. Basically, all these systems we have discussed have a Poisson arrival, and also the server is exponentially it's also Poisson. I would just say, and we see that like basically what we did for kind of analyzing all these systems, basically first trying to draw the state diagram and then solve the steady state probability, and with that find the average number of packets in the system or queue. Then we can use that to find the average wait time or delay using Ito's theorem. And of course, before even drawing the state diagram, we need to determine what are the states, and then we need to find the transition probabilities from one state to another state. Okay, I'd like to consider one more complicated example than the example we considered previously. Let's say we have a system with two kinds of packets. Two kinds in the sense that the arrival rates and the departure rates will be different. Like we have a red packet, like type 1 packet, with arrival rate lambda 1 and departure rate mu1, and we have a type 2 packet with arrival rate lambda 2 and departure rate mu2. And here's just one example. Let's say this is a queue, it's a little bit ugly, and there's a server is serving like a packet of type 2, and then another packet of type 2 is waiting in the queue after two type 1 packets are waiting. So now to analyze these systems, again, we want to first draw a state diagram for it. But before that, we need to determine what are the states. And actually, it's a little bit tempting at the beginning to maybe consider the state is simply the number of type 1's packet, number of type 2 packets. But that's not sufficient, because what the state means should be like, given that you are in the current state and given the statistics is not changing, the subsequent statistics will be the same. Like in the sense that like we will expect, if I ask what's the average time that the next packet will departed, will be the same given two same state. But apparently, if I have these two different situations, let's say I have this one, instead of like two type 2 packets in the system and two type 1 packets in the system arranged this way, maybe I have this, actually the one is serving is a type 1 packet, and then like I have type 1 packets in the queue, and two type 2 packets in the queue, and so on. Then apparently like the average time I expect to have a packet leaving the system will be different. Actually, it's apparently it won't be the packets that will be leaving from the system will be even different. The first packet that will be leaving in the first case will be like a type 2 packet, and then the second case is a type 1 packet. So therefore, the state in such kind of system is really the configuration of the current queue here. For example, like not just that this will be a different state, and also a different order of this type 1 and type 2 packets will be different state also. Therefore, you can think of that should be like a 4C2 number of combination here, just for different different arrangement of this this four two type 1 packets and type 2 packets. So and apparently, if we think of this the 4 states, then we have a very, very complicated state diagram basically. And this is again like we have infinite number of states, and it's pretty bad that like for example I can have a state, maybe I draw like this. Now I write like I just ignore that whether it's a server because it's not important really. Whether like this state being served here, I mean this packet being served here is actually in the queue or not in the queue. What I mean is that I can just draw a queue here, one single queue, and maybe I can represent this the same as this one here. And if this packet is served after a delta period of time, then my new state will be something like that. So, and the transition probability for that will be just mu delta as what we did like previously, or like should be mu 2 delta because it's a type 2 packet. And we can have, for example, in the next state, it can become something like this, have one type 1 packet coming in, and that, and this will be a lambda 1 delta transition probability. I mean I have one type 1 packet getting into the system, and so on and so forth. You can write down the state transition probability, but unfortunately it's almost too complicated. It is actually too complicated to find the steady state probability in this case. Okay, so what instead, like, okay, this is a problem that is actually too difficult to be analyzed as what we did previously. What we will consider now is a simple version of a very similar problem that, let's say, we also have two kind of packets, but let's assume that like instead these two types of packets are putting in a queue, it's more like that the two types of packet are putting in two queues here. So let's say whenever I have a type 1 packet, I will queue in this Q1 here, and a type 2 packet and queuing in the type 2 here. And I only have one server, but basically this server just arbitrarily pick a queue, and then we'll serve one of these two packets. And it pick a queue. If it turns out pick this one, it will serve at a weight like if we pick a packet type 1, it will serve at a weight mu1. If we serve a packet type 2, it will serve at a weight mu2. So if we have a system like that instead, then in this case, actually we can just use the number of type 1s and number of type 2 packets in the system as the state to represent a state of the system, represent the state of the system. And so we just need two numbers basically. Let's say 0, 0 will represent that there's no type 1 and type 2 packets in the system, and 0, 1 will be like I have no type 1 packets but have one type 2 packets, and so on and so forth. So if that's the case, then we can write down the state transition diagram for this simple version. Let's see, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3, and so on. So, let's say we start with like no packets in the system whatsoever, and there's a probability of lambda 2 delta that within the next slot that there will be a type 2 packet get arrived into the system, so therefore there will be one more type 2 packets, and so on. If we start at a state with one type 2 packets, the same probability lambda 2 delta that get into the type 2 packets arrived, and therefore like have one additional type 2 packet, and so on and so forth. Lambda 2 delta, lambda 2 delta. So therefore, like all these have this transition here. And similarly, if I can have start with like no packets in the system again. If I receive a type 1 packet, that is like I will receive a type 1 packet with the probability lambda 1 delta, I will move to the state 1 0. So I have lambda 1 delta like this. So all this will be lambda 1 delta, and so on and so forth. I'm not going to draw all this now. And then from state this is 2 0. Let's say from state 2 0, there's a probability mu 1 lambda that mu 1 delta that a type 1 packet is served by the server. So therefore we have a probability mu 1 delta get transition to the state 1 0, and so on. We have mu 1 delta like this, mu 1 delta, mu 1 delta, mu 1 delta, and so on. And if I go back here, I have mu 2 delta, and so on. Actually, you know that like the delta will eventually be cancelled. Yeah, I should have just why mu 1 and mu 2 instead is here or here. But anyway, you see that like whenever I go from right to left here, I have a probability mu 2 delta. From left to right, I have a probability lambda 2 delta. From up to down, I have probability mu 1 delta, and from below to up, from down to up, I have a probability lambda 1 delta. Okay, so that's the state diagram, and I can I'm not going to write down the probability here, but I'll just complete the diagram here like this. So now we can find the state transition probability. It's not exactly very easy in this case, but it's not hard also. One thing we know that or I don't not even think about that yet. Let's say we call this row as pi 0. Basically, what I mean is the probability of this whole row, some probability here. Oh, I'm sorry, I didn't even put in the steady state probability. Let's say the steady state probability for each of the state will be just pi 0, 0, pi 0, 1, and so on, pi 0, 2, and so on and so forth. Or instead of calling pi 0, let's call it p0. So p0 is just sum over pi 0 I from 0 to infinity, let's say. So p0 is the probability of this whole row here, to sum together. And maybe I can call P1 as the probability of this whole row here. Use red also. So now what happened is that if I look at what is getting into P0, remember that like all this pi ij steady state probability, therefore P0 should not change also. It's kind of like should be steady also. So if this is a steady state, by our previous argument, the probability get into this here, P0 should be the same of probability getting out of that. And the probability getting in here is what? It's just P1 times mu A or times mu delta, because all this going down is mu1 delta. So therefore it will be like P1 just times mu1 delta. Or like we can, I mean, if I go one more step, all the probability that getting into this P0 here is just pi 10 times mu1 delta plus pi 11 times mu1 delta plus pi 12 mu1 delta, and so on and so forth. And sum to pi 1 to infinity, basically mu1 delta. And I can pull out this mu1 delta out and sum over p pi 1 I equal to 0 to infinity. And we say that this actually is just P1. So therefore, like, the probability getting into this P0 is just P1. And getting out of that by the similar token will be just P0 times lambda 1 delta, right? So therefore what we get is that P1 is equal to lambda 1 over mu1 times P0. As usual, we will define rho1 as lambda 1 over mu1. So therefore this will be like rho1 times P0. Now I can do something similar here to look at what is getting into, let's draw this here, into this state here, the probability getting into this state here, will be just, I think you can easily see that, will be just P2 times mu1 delta, right? So I will have similar equation, basically P2 times mu1 delta, and the probability getting out of this whole green block here will be just P1 times lambda 1 delta is equal to P1 times lambda 1 delta, and this will give us P2 is equal to lambda 1 over mu1 times P1 on rho 1 times P1. And similarly, I will all have all this equation pk in general will be equal to rho k minus 1 times rho 1 times pk minus 1, and will be equal to rho 1 to the k times p0. Now, because like p are probabilities, what we get is we can normalize all the p, so we have sum over pk, k from 0 to infinity should be equal to 1, and this will give us rho 1 to the k equal to 0 to infinity, p0 equal to 1, therefore p0 is equal to, we know how to sum that, this is just equal to 1 over 1 minus rho 1, so p0 is just equal to 1 minus rho 1. Actually, we saw this before. This is exactly doing the MM1 query, and what we get is like pk is just equal to rho 1k 1 minus rho 1. And if we think of like this is like the whole row here, the sum of this whole row, this P1, P2, P3, and so on, these probabilities are equal to this thing here. Maybe I copy here. We just put it here. And I can also like look at each column, right? For each column, the probability, let's say call it a P, maybe call it Q here, QK. Let's say if the K column, this is the third column for QT here. And because like by symmetry, apparently, this Q, this is Q3, this is Q2, and so on. In general, QK will be just equal to rho 2 to the K 1 minus rho 2, where rho 2 is just equal to lambda 2 over mu 2. Now, what I'm going to do is like, we see that we have the sum probability of this guy here along the same column have this form here, and along this row is this form here. If I look at each of these particular state probability, let's say if I want to consider pi jk, it will be in the jth row and the kth column. So it's like if you think of probability, it's in something and also in something. Therefore, if we assume that these two events are independent, then the probability will be just the product of the probability, right? So of course this is not really a rigorous argument, but I will just guess here, make a guess that this pi jk is just equal to pj times qk, or equal to rho 1 to the j 1 minus rho 1, rho 2 to the k 1 minus rho 2, and I would guess that okay, this will be the steady state probability. And what I need to do is I need to verify that indeed it's a steady state probability. And what we can do is that we will use the same equation that we have. I don't think we need this anymore. Let's erase some of this so we have space for that. So what we're going to do is we'll just recall that like for any states, let's say pi s here, and this is like the probability of the state s. And let's say this is the steady state probability. Then it should satisfy that this should be equal to pi s pi times transition probability s pi times s, sum over all s pi. Because we can think of like, if it's not steady state probability, the expression on the right hand side actually compute the probability of pi s, of probability of s in the next state. And if it's steady state probability, then the probability in the current state will be equal to the probability in the next state. So therefore, like the left hand side will be equal to the right hand side. So okay, now let us verify that. Let's say we have this pi jk, just any probability here is pi jk, and we look at the transition to pi jk. That would be let's see, we'll have probability yeah, actually it is even easier just to think of like a state pi jk here, and we look at the probability getting out and getting in is the same. If it's the same, then okay, okay. I see. I forgot one thing actually. I'm sorry about that. Instead of verifying that, another way to verify that is using the so-called detailed balance equation. So it is a very simple concept. Basically, if you have the state transition diagram, actually every state are in pairs, then if the pair are balanced, in the sense that, like, if we look at each of the pair here, this going to this direction is equal to from this state going back to this direction here. If that's the case, then apparently, if this holds for all the pairs of this probability flow, I would say, then the probability that we are considering will be steady state probability. This is kind of very much obvious, because if was for each of these pair is kind of balanced, then if we arbitrarily pick a state here, and then let's say what is the probability getting out of the state and probability getting in of the state, it will be always equal, because like for each pair they are balanced. So therefore we only need to check with the detailed balance equation. Of course, this is a much stronger condition, in the sense that you can have steady state probability that does not satisfy the detailed balance equation, but still be a steady state probability. But if probabilities that satisfy detailed balance equations, then it has to be steady state probability. So okay, what we're going to do is we'll just verify this pi j key here and make sure that it satisfies the steady state probability detailed balance equation. So for pi jk, and let's say each transition to, let's say, pi j k plus 1, there will be from this state jk to jk plus 1. This transition probability is basically lambda 2. Wait, let me omit the delta here because it will get cancelled. And this going back here is mu2. Now I want to make sure that this lambda 2 times pi j k is equal to mu2 times pi j k plus 1. And apparently it should be, let me pull this thing here, that would be easier. Or maybe I pull this here. So now this pi jk, as we said, is just equal to rho 1 to the j 1 minus rho 1, rho 2 to the k 1 minus rho 2, and this one multiplied by lambda 2. Okay, this one I shouldn't have said writing equality, yes. Just put a question mark here. And the right hand side is mu2 pi jk plus 1 is rho 1 j 1 minus rho 1 row 2k plus 1 minus row 2. And as we can see that this mu2, if I divide mu2 on both hand side, I get like lambda 2 over mu2 on this side, and this is just another row 2 here. And then apparently this will just give me row 2k plus 1, and this is equal. So apparently because things are symmetric, and therefore it will hold for the other direction also. Therefore, the theta balance equation in this is satisfied, and therefore it's really the steady state probability in this case. So therefore, like with this steady state probability as this one, again, like we can do whatever we did previously. For example, we can find what's the average number of packets in the system, or maybe just average type 1 and average type 2, and then compute the delay, and so on and so forth. Okay. I guess I'll skip this one and just leave you as an exercise that part.